The average height of a basketball player is 6.5 feet. A random sample of 45 players found that the average was 6.7 with a population standard deviation of 5 inches. At alpha equals 0.05, is there sufficient evidence to conclude the mean heights differ from 6.5 feet? So for our first part, we have to write down the null hypothesis. And this is going to be that the mean is equal to something. In this case, we're talking about a height of 6.5 feet. There's also a slight problem with this question because it gives us some stuff in feet, but it gives us a standard deviation in inches. So we can convert the standard deviation to feet or everything in feet to inches. I'm going to convert the standard deviation to feet when we need to. So we're going to say that the mean is equal to 6.5. And then for the alternative, it says right here that we're looking to conclude that the mean heights differ from 6.5. So that means that the mean is not 6.5. This tells us that it's a two-tailed test. And since we're trying to conclude this means that this one is the claim. Now let's pull the numbers out of the problem. So the first number is the mu naught, or just the population mean. That's going to be 6.5. Next up, we need the population standard deviation, which is going to be 6.7. And because this is a population standard deviation, we know we are going to be working with, it's not 6.7, it's 5. Now in this case, it's 5 inches. And so we know that there are 12 inches in a foot. So 5 over 12 will put us back in feet. Because we are given the population standard deviation, we know we're going to be doing a z-test. This conversion, I'll cover a little bit more right here. So we have 5 inches. We want to go to feet. So if we multiply it by 1, that's fair, right? Because 1 times anything is itself. So there are 12 inches in 1 foot. The inches will simplify out and we'll be left with feet, which will be 5 over 12, which is why this is 5/12. We have a sample size of 45, so n is 45. And we were told that the sample average was 6.7 feet. So x bar is 6.7. And then we're given an alpha of 0.05, level of significance. I've done so many of these questions with an alpha of 0.05 now that I have memorized what the critical values for this are. This gives us a critical value of plus or minus, since it's two-tail, 1.96. I will show how to get this. I just happen to know this off the top of my head at this point. So let's go ahead and do the next step, which would be compute the test stat. So the test stat is going to be found using the formula x bar minus the mean divided by sigma divided by rad n. If we plug in our numbers, x bar is 6.7, the mean is 6.5, the standard deviation is 5/12, so this is 5 over 12 divided by the square root of 45. We're going to put this in our calculator. So I'm going to go ahead and turn this on. We're going to type a fraction. 6.7 minus 6.5 over. We're going to type another fraction. 5 divided by 12. Whoops, I put 15. 12 over the square root of 45. We're going to hit enter and we get 3.22. Now that's how you do it with the formula, but you can also do it using the calculator. If you go to stat, go over to tests, and then z-test. We have statistics. That's what all of these are. So we're going to go to the stats option. and we're going to put in our values. So we have 6.5 for mu naught. For sigma, we have 5 divided by 12. The calculator will figure it out for you, see? And then for x bar, we have 6.7, and n is 45. Our mu naught is not equal, our alternative is not equals to. So we pick the not equals to option, and then we hit calculate. You see we get the same test stat as if you round it. Even when we computed it, we got the same thing. And we get a p-value as well here. So we get a p-value of 0.001, and then I'm going to go ahead and round 13. And then the rest of the stuff we can kind of ignore. Now, if you want to get the p-value without using the calculator, you can use the chart. So this is saying that the area covered by this test stat is this value. So if we just look up this test statistic on the z table and find the area that covers, that'll be the p-value. This p-value is for both tails though, because this is 2 tail. And so we'd have to multiply whatever we get by 2. So we're going to go ahead and look at 3.22 on the standard normal chart. And it's negative 3.22. So it's this value right here, 0.00064. So we're going to come back and write that down. We get 0.00064. And in order to get the p-value, the entire p-value, so this is only half of it because it's a 2-tail test. So we have to do 0.00064 times 2 to account for both tails, the left and the right tail. And we get 0.000, and then if you round, it'd be 1, or 0.00, and then you round 13. So this is why that's the p-value. So if you use the chart, this is the process you would do. If it was a 1-tail test, then you would not need to do, this doubling. But because it's a 2-tail test, it splits stuff in half. So, okay. Once we have this figured out, we need to make our chart. So the chart looks like this. And then we draw a normal distribution on it. In the middle is 0. And recall this is a standard normal chart because we're going to be plotting z-scores on it. Standard normal charts always have a mean of 0 and a standard deviation of 1. So we need to put our critical values on here. So there's going to be some to the left and some to the right since it's a 2-tail chart. And in this area is going to be half of 0.05 because our level of significance is 0.05. So that means this means that 5% of the curve, if it lands in that 5%, then we think that the null hypothesis is wrong. If it lands anywhere else, then we think that the null hypothesis was right and it was just random chance from our study, right? Because we only studied 45 people. And so we'd say, well, it's just because we studied 45 people. But if it lands out here, we say, this is so far away, it appears that this is wrong. So we take our alpha, which is the 5% of the curve, and since it's 2 tails, it could be above or below this middle. So it's half of that. And so this area right here is 0.025. You could take 0.05 and divide it by 2. You get 0.025. So this is 0.025 on the top and on the bottom. So we need to find the critical values that go with this. Now I've already got them written up here, but the way you would find it is you would go to, you would find it according to the distribution. So we're using a z distribution. So we're going to go to the distribution table. So we're going to hit second distribution, and then we're going to go to option 3, inverse normal. We can give it an area and it will give us a z-score back. For our area, it's 0.025, and since we're dealing with the standard normal curve, the mean is 0 and the standard deviation is 1. We go ahead, we hit paste, and we get 1.96 plus or minus, because we did this lower half because this gives us area to the left. And so since the curve is symmetric, we would just put the negative version here and the positive version here, which is why I have them both up here. So this is negative 1.96. This is positive 1.96. And then we would say Let's say that you wanted to find this value using the chart. Maybe your teacher doesn't let you use the calculator. So you could go to the chart and find 0.025 on the chart. So if we open up this chart and find 0.025, it is going to be right here. You want to find the number that's closest to it. Sometimes you just have to pick one that's really close to it because the number you're looking for might not be on here exactly. But you see this is negative 1.9, and if we go up, it goes up to the value 6. And so it's the same thing, negative 1.96, and then you can say by symmetry, you can take the negative and the positive version. Okay, now we can make our decision by plotting the test stat or using the p-value. So let's do the test stat first. So plotting the test stat, we got a test stat of 3.22. It was really big. And so that would be up here, 3.22. This is the test stat Z. And so we'd say it landed in the shaded region, which is too far away from the middle for us to reasonably accept H naught. So we would say that we reject H naught, reject the null hypothesis. And then we'd say that because of our study, we have evidence to say that, hey, we think the other thing is right, but we got to look at what our claim is, because we always talk about the claim. Well, our claim is the alternative hypothesis, which we think is right. So we think our claim is right based on the study we did. So we say we have evidence, which is our study. We have evidence, or there is evidence, to support the claim. And then you would continue going, and then you would say something like that it differs from, the average height differs from 6.5. And that would be how you make the decision using a z-test. You could do it with a p-value as well. You would say that here's p-value is 0.013 and alpha is 0.05. And then you would say that alpha is greater than p, meaning that the test stats p-value has to be inside of alpha. It's smaller than alpha. So like the shaded region of that would be smaller. You see, it would be like this area right here in purple. It's smaller than the bigger shaded region. So we would say that, oh, this is evidence to reject. So without even graphing, you could do this using just the p-value method, and you would reach the same conclusion. Reject the null. We have evidence to support the claim that, and then you would say whatever it is you're trying to conclude, which is we're trying to conclude that the mean heights differ from 6.5 feet. And that's how you do a question like this. So not too bad. There's a couple different ways to do it. So I showed a bunch of different ones, a bunch of different ways to get the same answer, so you can check your work as you go. If you have any questions about this, let me know, and we'll catch you in the next question.